So anyone is staying in campus right now, or all are at their home? No one is responding.
So what, sir?
I'm just asking like if anyone is staying in campus.
Some people, I guess, sir.
Pardon? I couldn't hear you.
Sir, actually, two people are staying in campus, sir.
Oh, okay. I mean, yeah, already 20 people have joined till now. We'll wait for 1 or 2 minutes more and then we will start the class. So everybody knows that, right? The class is going to happen today from 9:30 onwards.
Yes, sir. Yes.
Okay. Okay, so now we'll start with the class. Maybe let others join in the meantime. So today we will have the first class on mechanics of solid. And myself, I am Grieger. So I am a new faculty from civil engineering department. Uh, Actually, in this today's class, we will have some review from your previous course, like the engineering mechanics which you have done in your second sem. Uh, so anyway, before going to that, we will just like this is what I am planning today. We will have some outline of this course with some introduction, and I will explain what is normal and shear stress, what is strain, and what is some numerical examples. If you have any doubt in between, you can ask. You can stop me, and you can ask any doubts. No issues in that. So this is the syllabus. I think you might have you have these data, right? The syllabus and some references and what are the learning objective, the course outcomes, etc. Uh, Someone can reply. Hello. Hello.
Yes, sir.
Yeah. So I'm just asking you like whether you have this data with you right now, like the syllabus and all.
Sir, no, sir, I think.
Okay. So at present there are only 20 people. So is it like that, like for
Sir,
online class?
no. Sir, there are 20 presenters and the attendees, there are 18, sir. Totally 38.
Okay, okay. 20% and
If you scroll down, there will be 18 attendees.
okay. So total 30. Okay, fine.
Yes.
Okay, so in module 1, we will say about what is a simple compound and thermal stress. the composite bars, then strain energy, principal stress and principal planes, and then we'll finally end with Mohr circle. So actually in compound and thermal stresses, you need to know what is basically meant by a stress and strain. Actually, it was meant to be supposed in your taught in your engineering mechanics class, but I think we'll have a review about that area, what is stress strain. So that's what I'm planning to do today and in the next class also. So these are some of the reference books. Actually, there are, like, if you search for mechanics of materials, you can find plenty of books online. So you can refer any books, and this is actually like a foundation stone for many areas. And this is a grading policy. Assignments will be 50%. Then cycle tests will be like 10 marks each. 2 cycle tests will be there, and end semester exam will be 30 marks. The number of assignments, it may like we have to decide like how many. Minimum there will be 5. Yeah. Okay, so let's start with the introduction. So this mechanical solid is basically like a branch of applied mechanics that deals with behavior of solid bodies subjected to various types of loading. So in engineering mechanics, which you have done in your second sem, you have studied with respect to rigid bodies. So can someone tell me what do you mean by a rigid body motion? Hello?
Deformation is zero, sir. After applying force.
Okay, deformation. Okay, that's okay. The fine. Yeah, that is true. The proper definition of a rigid body motion is like if you take any 2 points in that body. So after applying the load, the distance between that 2 points will remain same. Like it will not change. So ineffectively, the body is not going to deform. But in so we have you dealt with this type of rigid bodies in engineering mechanics, but in this course in mechanics of solid you are going to deal with deformable bodies. So I mean by deformable means elastic bodies mostly. So what happens to the like suppose if if there is any applied load happening on that structure, what happens to the deformations? Deformation in the sense like stresses, strains, displacements, etc. So some examples like there will be bars with the axial load, shafts in torsion, beams in bending, and columns in compression. Actually, we will be dealing with these 4 cases in 4 separate sections. Like I think one of them is like each will contribute to each modules actually. So the basic objective is to find stresses, strains, displacements in structures and their components due to the load acting on them. So why we are doing this type of analysis? What is the main goal behind finding the stress, strain, etc.? Because in actual design, an engineer should consider both dimension and material property, and as a result, the structure should not undergo failure. It means that if we are designing a structure, we should always focus on ensuring that the structure is not having, like, it is not exceeding a permissible stress or strain displacements. Suppose if I say like, okay, my beam should not deflect more than say 20 mm displacement, like if you are calculating the midspan deflection of a beam and you are saying that you are putting the constraint that if the beam is deflecting more than 20 mm, the beam is a failure. So how do you calculate that midspan deflection? So or there are some other factors like the stresses. The stresses should not rise above a permissible limit. The strains, displacements like that. So for the safe design of any type of structure, we need to understand the mechanical behavior. And in order to understand the mechanical behavior, we need to find the stresses, strains, and the displacement, these mechanical properties associated with these structures. And that's where this mechanics of solid comes. And when you notice that this mechanics of solid is just like a foundation course for many areas in civil engineering, aerospace, mechanical engineering, or even I think the petroleum, offshore structures, etc. For everyone, this is a basic course because this has application in all these areas. And understanding this course will give you more idea about advanced topics in structural engineering. Because whatever things you are going to learn in your next semester onwards, like next semester you will be learning about analysis of indeterminate structures, then advanced structural analysis, like that, metrics method of structural analysis. So every courses, it like everything starts with this course, this mechanics of solid. Basically, I should say it started with engineering mechanics, but now from engineering mechanics you have advanced to this one, and now this will be the foundation stone for the other courses. So what I want to say is you should be thorough with the basic concepts in the from this course. And so here the idea is actually very simple. You need to understand some concept, and then after that you have to apply the same concept in theoretical applications. Yeah, that's the part. So let's start with some assumptions which we are following in this course. Basically, we assume that the material is elastic in nature. So by what do you mean by elasticity? Elasticity means that the material can regain its original shape and size even if the applied force is removed. And the second property is, a second assumption is, the material is homogeneous. Homogeneous in the sense like every particle of the material possesses identical mechanical property, and the material is isotropic also. That the same property in any direction at any point. You have learned about what is heterogeneous and homogeneous, what is isotropy, anisotropy, etc. from your school time. So anyway, these are some assumptions which we are using here. And if you violate any of these assumptions, then the theory behind developing the principles also will change. So when you go to the advanced courses, actually, basically what happened is like either you will be dealing with inelastic body, sometimes you will be dealing with homogeneous. Instead of homogeneous, you will be dealing with heterogeneous material, and similarly, instead of isotropic, you will be dealing with anisotropic material. So let's start with what is the definition of a stress. So let's start with a prismatic bar subjected to axial forces. So what do you mean by prismatic bar? Prismatic bar is nothing but a straight structural member having same cross section throughout its length. Like if you cut a cross section at any point, at that point the cross section will be same. Like if you are taking at any point along the axis, and you are assuming that the axial force is acting on that bar. So axial load is nothing but a load directed along the axis of the member, which results in either tension or compression. We assume that this axial force acts along the centroid of the cross section. Suppose this is the cross section here, then the centroid is the center point, and at the centroid of this, we are assuming that these axial forces pass through the centroid of the cross section. That's one assumption we are making here. So how to find the resisting force developed here? Okay. In order to find the resisting force, we just take this. We have studied in your engineering mechanics. Like we will cut the bar into two equal parts. It's not necessary two equal parts. We will cut the bar into two parts, and so this is the one half. This is the second part, and at this part there are some unknown forces acting here, and we will assume that the body is in equilibrium. So in equilibrium, we can say that the summation of forces will be 0. So the load acting here, the one external load acting here is P in the outward direction, and this is internal forces developed here will be the reaction, which will be equal to P. So now we can define stress as when a material is subjected to an external force, the resisting force is set up within the component. The internal resisting force per unit area acting on the material is called stress at that point. Once again, the internal resisting force per unit area. So stress is defined as the force acting on the unit area. So which is nothing but R by the cross-sectional area. Suppose A is the cross-sectional area, it will be R by A, or R is equal to P here. The external load and the resistive force are same here. So the stress is nothing but P by A, the ratio of the external load to the resistive area. So mathematically we can write stress as limited delta A tending to 0 delta P by delta A. So what does this mean? Again coming back to this figure, here we consider a small area, delta area, and we will try to find what is the area acting on that region. So we take the ratio delta P by delta A, and we assume that this delta A tends to 0, and we will get dP by dA, the theory behind the derivative part, and from that we can find the total load as integral of sigma dA. Here we are again making another assumption that the stresses acting on the cross section are uniformly distributed over the area. What does that mean? See, here I am applying a load at one support and assuming that the stresses developed, like the load acting per unit area, the stresses developed are same, like whether it is point at this point or whether at another point or at the center, everything is same throughout that cross section. So what happens if that load, if that assumption is not there? We will see in the next slide. So we consider an average stress where the total load divided by the total cross-sectional the cross-sectional area, that is defined as the average stress acting on the at that cross-section. So what will be the unit of stress? So the numerator is the force, which is expressed in Newton. The denominator is measured in square meter squares. So the stress will be nothing but Newton per meter square. So this Newton per meter square is known as Pascal. And 1 megapascal is nothing but 10 raised to 6 Pascal, which we can write as 10 raised to 6 Newton per meter square. And if we convert this meter into millimeter, then it will be like 10 raised to 6. In denominator we will have another 10 raised to 6, and numerator and denominator will cancel each other. So we will get 1 megapascal as 1 Newton per millimeter square. So in design codes and all, these notations are commonly used. This megapascal and this Newton per millimeter square. So as I said, what happens? The stress developed is not uniform at any cross section. Suppose if we have a if we have a bar subjected to axial load and we are applying some tensile force in both the directions. Okay. So the stresses at away, like at the stresses away from the ends, it will be uniform as shown in this figure. Okay. But the variation of the stresses near the end, like the close to the point of application of the external load, it will be non-uniform. For example, like at the center region, it will be more, and when it moves towards the end, the stresses get reduced. The resistive force get reduced. I mean, the resistive force developed in that region. It is also applicable in a plate with a hole. Suppose if you have a plate with a hole in the center region, and this plate is subjected to tensile load at the 2 points. Okay. Then if you are trying to plot the stress distribution near the hole, then you can see that this region will have more stress compared to as it you moves away to the end regions boundary. Stresses are classified into two types. One is the normal stress and other one is the shear stress. So normal stress means that it acts in a direction perpendicular to the cut surface. And normal stress are two types: tensile stress and sigma stress. Sorry, tensile stress and the compressive stress. So tensile stress is denoted by sigma t. Okay. So basically, the bar is subjected to pulling forces. Like what we are trying to do here is we are trying to elongate the bar. So there will be two forces acting opposite, one towards the left side and other to the right side, and it tries to elongate this bar, and as a result the resistance developed per unit area at any cross section is termed as tensile stress, and the maximum tensile stress the material can resist is termed as the tensile strength. Similarly, if instead of a pulling force, suppose if we are pushing towards each other, see the load P is pushing to each other, then what it tries is to shorten the bar, like the length will reduce. As a result, the internal resistance developed per unit area is called compressive stress, and the maximum compressive strength, sorry, the maximum compressive stress the material can resist is termed as compressive strength. Compressive stress and
Sir,
compressive strength. Yeah. Hello.
sir, I have doubt in distribution of stress in the previous slide. So in this whole one, there is stress in plate with the hole.
Okay. Yeah.
How this distribution is done in whole one figure?
The thing is like as you move, see the load is acting at this region.
Yes, sir.
This point. So just similar to the same area, I mean the same, just like a without a hole. When you see that at the point of the at the point of acting of the load, at that region, it will have the more stress developed there. And when you move away from that region,
Yes, sir.
so the resistive force developed will be slightly less. So the same concept behind drawing this figure, the same thing applicable here. Like at the point of application of that load, for example, like at this point, the more stresses will be developed here. And suppose if you are applying the load at this point, then the figure might be different. Like this maximum might be developed at this region instead of this region. And when you move towards the, when you move, like when you are moving away from the application of the load, we assume that the beam is like the stress is developed uniformly, and that is because we made the initial assumption that the beam is elastic, the beam is uniform, sorry, the beam is homogeneous, and the beam is isotropic.
Yes, sir. Okay.
Yeah, and overall, sometimes the maximum stress developed at this region can be like 2 to 4 times the average stress. The average stress is nothing but the uniform, the uniform stress developed in the any cross section. So sometimes the maximum stress developed can be say like 2 to 4 times the average stress.
Yes, sir.
Okay.
Sir,
Yeah.
sir, the hole in that plate has any effect on the load, that stress distribution? Does it have any effect, or is it simply the same way as that the simple plate?
No, it will not be the same, because the thing is like you are removing some material from here. So so what is a resistive force means? The resistive force is something developed by the just like here. See, the load is applied on the structure, like the external load is applied on the structure, and the stress is induced in the material of the structure. So when you remove some material from the plate, so basically you are trying to the stress developed will be different. For example, like suppose even if you apply same load P, the maximum stress developed at the center may not be the same as in the two cases, like in the bar or in the plate. It will be different because you are removing some material, and that removed material has actually some contribution towards the stress developed in that region.
So, sir, can we say that removing a material causes less stress developing at that point, because some material has been removed, so restoring force causing material has been removed, and this causes less stress to be produced on
Yes.
application of force.
Yeah,
Okay,
yeah,
sir.
that is true. Yes. So that's why like when you put a screw, actually I have an example later part. So when you put a screw, when you drill a hole or something in the plate, you should be checking about the shear modulus, the shear stress, whether that plate can hold the with that drilling part. Sometimes this plate can break because of if the drilling force is more.
Okay, sir. I got it.
Okay, so we have done with normal stress. Normal stress are two types: the tensile stress and compressive stress. Where the normal stress, force is acting perpendicular to the cut surface. So we have the section like this, and in that section, the external force is acting perpendicular to the surface. Now we are moving to the shear stress. In shear stress, the applied force acts parallel to the plane of interest. Suppose if you have say two rods as shown here, and you are using a screw to join these two rods, and these two rods are subjected to some tensile forces Q. Like this rod you are pulling to the left side, this rod you are pulling to the one rod you are pulling to the left and one rod to the right side. So what happens to the screw? Like what will be the stress distribution developed inside the screw? Suppose if you take a cross section of the screw at this point, and if you draw the free body diagram of the screw, then you can see that this load Q is acting parallel to the cross section here, in opposite direction in both the free body diagram. So we say that when the applied force acts parallel to the or the acts tangential to the cross section, we say it is a shear force developed in that, or not the applied force, so the resistance developed. It is called the shear force. So the resistance, okay, yeah, I have written here actually. The applied force is trying to shear off a particular section of the element, and the resistance developed for unit area along that section is called the shear stress. And you can find the shear stress as again the ratio of the shear force to the cross section area considered. And the maximum shear stress that material can resist is called the shearing strength of the material. So when you try to drill a hole for fixing screws and all, you should first check what is the shearing strength of the material, and then you have to apply that much of load for drilling that hole. I will show an example later in today's lecture only. And now with this we are moving to definition of strain. So I have a bar here. I am applying a load. So the bar is having an initial length L0, and when I apply a load P to the right side, the bar elongates. So I am applying a tensile load. Okay. If I am applying a compressive load, the bar shortens. So I am applying a tensile load here, and the bar elongates by delta L. So I am defining strain as change in length per unit length. So mathematically, epsilon will be delta L by L0. Not that I am using the original length. I am not using L0 plus delta L like the final length here. Change in length by the original length. And we can see it is a dimensionless quantity. The numerator and denominator both are measured in meter. There are some instruments like extensometer, electric strain gauges, etc., which can measure this strain with a magnitude of say 100 or 1000 thousandth of a millimeter. And we have some in our department we have machines like UTM, universal testing machines, where the bars can be subjected to forces of 1000 kilo, like more than 1000 kilonewton, and we can measure what will be the elongation developed in that bar. So again, similar to the types of stresses, we have different types of strain. For example, like tensile strain, compressive strain, etc. So tensile strain is nothing but the applied force is tensile in nature. Like the okay, just like as shown here, we are applying like a tensile force here, which results in the elongation of the material, the original material. So epsilon T will be increasing length by original length. So delta L by L0. Whereas this compressive strain will be happening when the applied force is compressive in nature. Just a second, can you give me just 1 second? Hello. Sorry for the interruption. Yeah. So the compressive, okay, we are having this tensile strain and compressive strain. So the compressive strain is nothing but when the applied force is compressive in nature. So what happens? Like when you apply compressive force, you are trying to will be a reduction in the length, and it will be minus delta L by L naught epsilon C. So in general, tensile strength is taken as positive and compressive strength is taken as negative, and these two types of strains comes under the classification like linear strain or longitudinal strain or axial strain, in the sense like the force applied is axial in nature, like along the longitudinal axis. This is because we are having another type of strain called the lateral strain, which we are coming in the next slide. So now we are having another strain called the shear strain, analogous to the shear stress. So in shear strain, as I said before, the stress here the force is acting parallel to the surface. So we are having the we are having the suppose we are having we are having a bar, and then we are applying a load tangential to the surface, this surface, and it is undergoing a deformation. This deformation shown in the dotted lines. Then we are calculating this delta, like the lateral displacement of the upper surface of the element relative to the lower surface. This ratio of the this quantity delta with respect to the distance between these two faces, it is known as the shear strain. Usually the shear strain will be very small, such that we can assume that for example like tan gamma like equal to delta by L, and with that assumption we come to delta gamma equal to delta by L. That is because the shear strain developed will be very small. So here we have to note that the load is acting parallel to the surface in which we are considering. There is another thing called volumetric strain. Volumetric, like when a member is subjected to stresses, it undergoes deformation in all directions, and as like there will be change in volume. So the ratio of change in volume by the original volume is called as the volumetric strain. And again, it is like a dimensionless quantity, and it can be shown that this volumetric strain is the sum of strains in three mutually perpendicular directions. For example, like total volumetric strain will be the strain in x direction, strain in y direction, strain in z direction, and again, if it has to be true, then we have to follow the property assumptions which we have taken initially, that homogeneous, those property, elastic not required, but homogeneous, isotropic, those things. Okay, so we move to lateral strain now. So as I said before, we have the longitudinal strain, where longitudinal strain, the ratio of the axial deformation to the original length of the body is taken. Now, when a material undergoes a change in length, suppose if I am trying to pull this bar, then obviously there will be delta increase in the length of the bar. But at the same time, if you look the cross section, it is show in the cross section the depth of this bar actually decreases. Initially it was B, and now in the dotted line it becomes B dash. So when we consider the longitudinal strain, we consider delta, the ratio of this delta by L. But lateral strain considers this change in this depth, like along the lateral dimension. So it will be B dash minus B by this expression, the original lateral dimension. And at the same time, so this is the bar subjected to tensile load, and suppose if we are subjecting this bar to compressive load, at that time the original B now becomes larger, like B dash should be larger than this B. Okay, so the thing is, if the longitudinal strain is tensile, then the lateral strain will be compressive. For example, if you try to elongate here, the longitudinal strain will be delta by L, that is a positive quantity. But if you consider the lateral strain, that becomes a negative quantity here. And similarly, vice versa also. Like if it is longitudinal strain is negative, compressive in nature, then the lateral strain will be tensile in nature. So with that, we can define Poisson ratio. Poisson ratio is nothing but the ratio of the lateral strain by the longitudinal strain. But at the same time, we should define the Poisson ratio with respect to the elastic limit. We should say that the ratio of the lateral strain to the longitudinal strain is a constant for a given material when the material is stressed within the elastic limit. So I have to explain what do you mean by elastic limit. I will explain in detail in the next class, but what you have to understand is if we have any structure or any material and if you try to apply a force, and you can see that to some extent like if you apply and when you remove that force, so when you apply force the body deforms, and when you remove that force the body comes back to its original shape. But after some say certain force, permissible force, then the body cannot come back to its original shape. So that limiting force is called the elastic force, and the property of that material is called elasticity. So within this elastic limit, the Poisson ratio is defined, and we can see that the Poisson ratio appears to be a constant. That is the ratio of the lateral strain to the longitudinal strain. Okay. And for steel, the Poisson ratio is almost like 0.25 to 0.33. Concrete, roughly about 0.15 to 0.2. Rubber, it will be 0.45 to 0.5. And you can see that in cork, this Poisson ratio, the cork which we use for filling the bottles, closing the bottles and all, the Poisson ratio will be nearly 0. So what is the implication of that? So like the cork can withstand, like the cork can withstand the forces developed inside the bottle. Okay, so that's one thing I want to add here, and then yeah, what's the time now? Okay, 10 minutes. So we have some 2 examples. I hope everyone have a calculator, and this question you won't require any calculator, you can do it like directly. So a rod 10 mm by 10 mm cross section is kilonewton. Calculate the tensile stress developed. This one you might have already done in your school time, like finding the pressure. As you noted that the pressure and stress have similar units. So sigma T will be P by A, and you are calculating, it will come as 200 MPa. I'm just leaving that. And another one, an axial compressive load 10 kilonewton is applied on a rod of 100 millimeter in length. The final length of the rod after application of the load is 98 mm. Calculate the compressive strain developed in the rod. So the compressive strain will be the change in length by the original length. The change in length is 98 mm minus the 100 mm. The original length is 100, which is 0.02. Now I want this. Yeah.
Sir, in the first question, it should be 10, right, sir? 10 into 10 power 3 Newton, not 20, I think.
Okay, good. Yeah, actually, yeah, that's correct. Yeah, actually, this is wrong. Yeah, this is 20 actually. Come on. Yeah, now it is correct, right?
Yes, sir.
Thank you for noting that.
Sir,
Now, yeah.
Sir, if I consider a cuboidal block and I'm applying tensile load of 20 kilonewton on both sides, so what should I consider the stress, the load for stress? Sir? Should I consider 20 or 40? Like,
No,
because
no.
a cross section will have both sides pulling at 20 and 20, no, sir.
No. Actually, the resistive force, basically our examples, like in our, everywhere, in the definition of the stress itself, we started with this problem. Like we are applying a tensile axial force in here in both directions, which is pulling this load in both directions, which is pulling the bar in the both the directions.
Okay, sir.
So at this region, so suppose if you want to measure the stress developed at this cross section, you are cutting the bar into two parts, and you are just using the equilibrium properties. You are trying to figure out what is the stress developed here.
Okay, sir. Okay, sir. Understood.
Sir, what will happen if unequal amount of forces are applied on both the sides?
Unequal amount. Okay. Then you can solve this question actually. This is based on that part. The bar is subjected to an external compressive load say 27 kilonewton. Locate the section where the normal stress is 0. Actually, everyone can try using a pen and paper. So we are having this bar. It is subjected to a compressive load here, and this bar is having a density. So there is a self weight associated with this bar, and we are asked to find where the normal stress is coming 0. So you can start with drawing a free body diagram. Take a section along this line. Assume that at this region the normal stress is 0. Can someone give some clue? Any clue?
Sir, 11 meters from the.
Yeah, I think 11 meters. I just need to. Yeah, 11 meters. So I hope you understood, right? So what we have to do here is we have to find the stress due to two parts. One is stress due to the external load P. That will be at this point the stress due to the external load will be P by A. And we have to find what is the stress due to the self weight. The stress due to the self weight will be the density times volume divided, that is the force part, and by area. And now we need to equate like the summation, like one is acting in this direction, other one is acting in the downward direction, and we need to do the summation of forces here. So ineffectively from that you can calculate excess 11.2 meter approximately. And another example, determine the force required to punch 20 millimeter diameter hole through 10 millimeter plate. The ultimate shear strength of the plate is given as 360 MPa. The diagrams are actually very bad. I just drew with PowerPoint. So just understood that there is a plate here, and this is actually going directly into the center of the plate. So the elevation part, it looks like this. So actually this is like slightly rotated, but it looks like exactly like this. First of all, like the previous example, anyone wants an explanation one more time? Hello? Are you busy with this question?
226 kilonewton.
Yeah, 226. So can you explain how you did it?
Sir, I took that stress equals to 360 megapascal.
Okay.
And force we need to find, and area is 2 pi RH.
Okay, fine. Yeah. Okay. So I will explain here. So basically, we have to do here is this length is the thickness of the plate, which is nothing but 10 mm, and the diameter of this hole is 20 mm. This is given here. So actually the figure is not up to scale. Sorry for that. So we are provided with the shear stress. So we need to find the force required, the shear force. So that is nothing but the shear area times the stress. So how do you calculate the area here? The area here is nothing but the not the cross-sectional area perpendicular to the surface. We have to find the area parallel to the surface, in the sense like we are going to punch this plate and there is a hole developed here. So we need to measure the area of the hole, the cross-sectional area of the hole. So in order to do that, we just take the circumference 2 pi d, 2 pi r, I mean the pi into d, and the thickness of the hole, we will give you the total shear area, and the force required will be sigma into the shear area, which is nothing but 226.2 kilonewton. Yeah, actually, what's the time now? Yeah, 10:18. Okay. Yeah, that's all for the today's class. I want some feedback from you. Like, do you prefer numerical examples also to be solved? Actually, we have to solve the numerical examples. So you want to say, like, you have any doubts or you want to ask something? No one has any doubt or?
So can you share the PPT, sir, with us?
Yeah, sure. I can share the PPT. And at the same time, can I get one more class in the sense like for conducting some tutorials, like maybe 1 hour in a week, afternoon section, any day?
So for
Some tutorial questions on this course.
okay, sir.
Anyway, from not this week, maybe next week onwards. Like after once we finish some courses, like I can give you some sheet, or maybe I can give you some tutorial questions. You can do it, and if you have any doubt, maybe we can have a discussion, like a common discussion. Maybe not in the class time, maybe like a 1 hour afternoon section, any of the days.
Okay, sir.
You think about it. Maybe from next week we can have, and we'll have this till me a common time. I will share the PPT here. Like if you have, do you have any doubts in this section?
No, sir.
Actually, this is not coming directly in our syllabus. This is just coming like this is a review part. This you have to these are all supposed to be taught in your engineering mechanics things. Yeah. So maybe like next class also it will be slightly review part, and then from next to next class onwards, like we'll have the continuation of this thing where we'll be dealing more with. So next class we'll be dealing with what do you mean by Hooke's law, what will be how do you draw the stress strain pattern of a steel, those things, and then we will move on to thermal stress. Thermal stress means like till now we are saying about applying a external load. Now the external load will be like a thermal load, and what will be the elongation developed in that case. Okay, yeah, that's all now. So I need to take the attendance, no? Okay, download attendance list. Okay, there is a file coming. Yeah, I got the attendance list. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.